the critical value, boundary conditions, bottleneck issues related to the operation or control, which need to be considered before we start working with the commitment schedule or any assessment of that. In line with which, we have some important constraints identified under the unit commitment schedule are namely like the first one, spinning reserve. As the name says, spinning reserve. It is a reserve excess generated energy in the power system readily available to extract to meet unexpected, contingent, sudden changes in the load absorption. It is an excess generation like that. Suppose we have a 5 generator. 5 generator are generating a certain amount which is in excess to the actual requirement and losses. If there is an unexpected growth of load, these generators which are tied together, committed, shall adjust the generation what they have in excess to meet that contingent change, rather than setting up, switching on another generator to feed that requirement. In that due respect, spinning reserve energy is one of the important spare energy in the operational aspects of the power system be kept in good amount. You may ask me, what should be the percentage? The percentage of the excess energy that you are exactly transacting and to be kept as a spare depends on power system, load, and their dynamics. Based on their relation, the power system operation and control shall exercise, study, and plan certain percentage of the power as an excess power to be kept as a spare. It means the generation shall be in excess to the requirement such that sudden change in load, it is addressable immediately with a due respect. Or it may be a sudden problem in the generator due to which the expected output from that generator we are not able to extract. Then what can be done? Among the committed generator, if it happens with the one of the generator, remaining committed generator must be able to cope up the shift down that has happened due to one of the generator. Loss of generation has to be cope up by remaining. That is a floating energy ready to absorb. We call it as spinning reserve. It has a great importance in the operational aspect. It is called a reserve fuel like. So therefore, we have one example in the upcoming slide which narrates how is that spinning energy really make a sense that a loss of generation, one generator going out of the control, is worked out without getting affected by the operation of the system. And other way, whenever that spinning reserve energy is deficit to a certain demand, this will become a bottleneck issue. So that operation of the power system should be such a way planned suitably that value of spinning reserve should be kept in mind. It will not be exceeded beyond that. If so, the aspect like demand management, curtailment of load, or setting up of new generation to cope up shall be planned. Before doing that, it is an aspect of managing the contingent changes with the existing generation and spare energy what it is being right now kept. So this is of greater importance. And there could be another question, which is that generator is named as spinning reserve generator. Which is that generator certain percent is given to which? What is by that number? It may be another question in everybody's mind. Definitely, the spinning reserve energy, what I am speaking, the generation what right now we have is to meet P balance. Let us say active power, P balance, plus excess generation, what is kept as a spare, is known as spinning reserve. This spinning reserve shall not be focused on only one generator. It should be spread around the generations available in and around the generating aspect. It may be like hydro generator we have. You have thermal generator. You have gas or oil fired or coal fired thermal plant. So you shall not concentrate the spinning reserve only on thermal, only on hydro. It is to be spread. Certain percentage of the planned spinning reserve should be allocated to few of the hydro generator, few of the thermal units, few of the other alternatives. Why it is being done? This is to avoid bottleneckness. We call it as a bottling. It is called, suppose you focus every spinning reserve energy only on thermal plant. Suddenly thermal plant shut down due to so many causes. Then where is your spinning reserve? Lost. That is the issue, that bottling. You are trying to concentrate it on only one side. If there occur a problem at that resource side, how can that resource deliver your actual power plus spinning reserve? This is a critical issue called as a bottleneck issue associated with the operation. The keyword bottling is referred. Then what is the solution for this? The solution is the spinning reserve amount, so much of megawatt which is to be kept, should be appropriately split into different proportions on a different energy generation setup. So that if one generation setup is out of your control, other is there to take care. If another is going out, the last is there to take. In this way, the spinning reserve allocation should be planned engineering point of aspect. This way, this is very important constraint. This is an issue. Without considering this unit commitment, if you take, probably commitment will end up with the unmet situation only. The next is minimum uptime. So this is truly concerned with the thermal system. As we are aware, thermal generating aspects involve lot of machinery, associated aspects, auxiliaries, which require a continuous process of one-to-one, and another. At the end, it becomes a steam with which the turbine is driven and you are able to generate. As and when the starting up of the thermal unit is considered, it is not just a key start. It requires several hours to several days. This is more important. We cannot switch on a generator simply like a key on and key off if I don't require. In that perspective, the warming of water, economization, steam generation, cooling, all these series of processes to be involved to get the steam of your required quality to be put into turbine for its operation. We cannot maintain that temperature of 500 degrees centigrade or higher. It's very larger degree centigrade, which definitely keeps the steam which is able to drive your requirement. Then, once it is brought into on state, from the cold start, room temperature, a particular setup is taken in gradual steps so that it has come to the working temperature and it is ready to combine operation with the synchronized system. Then it is ready. It is the minimum uptime. It means once it is up by several hours to days, I am keeping it online, generate my required megawatt, and now the schedule is before I decide to take it out. Because it is not intelligent to run all the system in the plant all the time. Then the first point, we begin with the unit commitment. It means to say, whatever is the way I begin the generator to start and generate, doesn't matter to me. But I should plan such that which is required, that is the one to be compelled. Once it is compelled, should run for me. Yes, minimum uptime means once the machine which is committed to generate and develop a power for me should be maintained minimum certain hour to certain days as on duration only. Before that duration, let's say 25 days. Once the machine is switched on, 25 days minimum, it should not be planned to switch off. This is an example. What is the meaning of this? It is called minimum uptime. Once the setup is made on, turned on, develop power for you, it should not be planned to switch off immediately before the duration specified by the manufacturer, because that is the economic duration. Till that time, if we run the setup, it is going to pay you back the work value. Otherwise, before it is to be turned off by certain duration, early to which if you plan and switch it off, it is not economic. Hence, minimum uptime is the time till that duration machineries need to be kept online to serve for the purpose intended. Any decision before that duration, if taken to shut it down, will not yield economic. Therefore, minimum uptime is very much important. How it is important? Imagine I have 5 generators. All the generators must be having such a criteria. Minimum it should be turned on for a week to 15 days. Then the second generator, 15 days to 25 days is the minimum. The third generator, minimum 90 days. Just imagine, when I am trying to make economic scheduling under the unit commitment, definitely it becomes necessary for me to combine them and decommit them as and when required. Before I decommit it, this issue comes into my mind. If I decommit that generator, will it be economic for me? How long? How far? I do not require it. Later I may call back that machine to combine and develop power for me, because it is switching dynamically. When it is required, I call for a generation. When it is not required, I decommit it. It becomes a peak value kind of load dynamics of the system. This becomes an issue for me. I cannot simply switch off, switch on, switch off, switch on. This itself becomes non-economical to operate. Hence, minimum uptime is the duration. Till that duration, once the system is kept online, should be maintained, perform its duty to make fuel economy and resources optimally utilized. So, similarly, I have another time. Minimum downtime. Let us imagine any machine which we have just taken up online, developing a power, and a decision has been taken. Once the decision has been taken for a falling kind of valley load, a certain generator has to be taken out of the combination, shut down, decision has taken. Once decision has been taken, planning that, later for so many days, this is not required, hence decision is to shut it down. Once the schedule is taken to shut it down, the next aspect which is important is how long you are not going to restart it. That is defined by the manufacturer called minimum downtime. Minimum downtime is the time till that duration the machine, once decommitted from the schedule, should not be restarted again. This is because, however, we have a startup mechanism of thermal unit, we have other way also cooling mechanisms to shut down it. Series of mechanisms which will cool down the working temperature to the room temperature or somewhere certain standing temperature. Till that additional investment is done to decommit it and maintain it. We call it as shutdown cost. The cost involved in shutting down or maintaining at a certain value other than requirement. This cost of investment is very serious. How long this generator we don't require? Because if you require it very soon, again a startup cost is involved. To start it, it is not simply a start by key. It is to heat up, burn the fuel and make it readily available for the online. So these two become very important aspects. During the shutdown, minimum downtime. Till that time, you are not going to call it again. The minimum uptime, once you have taken a decision to turn it on, till that time, you are not going to turn it off. Because economy of fuel, operational aspects are concerned with the machine. Minimum uptime to hold it on once decision has been taken to turn on. Minimum downtime once you have taken a decision to shut it down, not to compel till this time once again. Otherwise, it is a serious disaster because cooling and heating mechanisms require sequential processes. I cannot do it in a spontaneous manner. Hence, these two are a bottleneck issues concerned to thermal unit. It must be considered very carefully. Next one, crew constraint. Definitely, when we speak about thermal unit, It requires a lot of space, no doubt. The plant is not so small, few of the people can supervise, control and operate. It's so vast, covering a lot of space, lot of machinery interconnected, and supervision and operation is required. We require set of people working in a machinery area, Section B, Section C, with skills and sets available to them. The crew constraint limit, you cannot run a plant or a neighbor plant side by side by a minimum possible people. You require suitable specialized operating personnel to operate it effectively for its intended services. You cannot shortfall, reducing 10 men into 2 men can look after. 10 men working over there simply by 6 like that. You shall not do. This is a critical issue by having saved a cost of operation or a person who is being paid, his salary if you are going to save, this is going to cause a disaster on the other side. Crew constraint requires separate specific set of people by count to be assembled on working on an area to make it optimally operated or maximize its performance. We shall not simply take granted. In this due regard, crew constraint is also important. Transition cost. This is another important aspect when you are operating a power system. See, whenever the status of one unit is changed from, some transition cost is involved and has to be taken out. So, the transition cost, suppose the machine is taken shutdown, startup, load is reduced, load is increased. There is a transition cost. What we develop is the fuel what we burn. This burnt fuel will not be exactly paid from the customer viewpoint. So, they will be consuming the energy, they will be paying for that. This transition cost is operational changes what we incur into the system to keep it working for the requirement. This involvement of monetary investment from the resource when material viewpoint, this is called a transition cost. To increase the generation to met into your requirement, to decrease the generation as per the load. This incremental changes either towards the positive side or negative side, this kind of transition cost, which will not yield you. It will yield you once it settles to a certain value. Increase value pay for you. Decrease value pay for you. In between lower to higher shift, this is called transition. And higher to lower shift, this is called transition cost. For which there is a burning of fuel, usage of men material resources to meet that requirement. That cost which you incurred is a serious phenomena that should be considered. That's what is the issue. You cannot simply do frequently increase, decrease. That operational cost becomes a tremendous, which may cause you a monetary losses, etc. It has to be seen carefully. Then hydro constraints. Because the thermal plants, if I consider, they do require huge water. If I consider only hydro system, hydro plants are not only meant for electricity generation. Basically, they are meant for the overall growth of the country. Sustained growth of the country is meant by hydro generation setup. That's how you can say hydro projects are multi-purpose projects. They are basically providing support for the irrigation and other sanitation or anything other like that. So it means to say, it is not the only intention that electricity generation from that. From the other side of it, hydro resource shall be effectively utilized for agriculture, irrigation purpose and other things. So there is an issue. I cannot simply generate because I have a surplus of storage or in a catchment, I can generate and do. The other part of the exit water, tail race water, may affect the flora and fauna habitants on the other side. So it is how, it is not simply to do it however we take a decision. Decision has to be taken with the perspective of multi-objectives. Hence, this hydro constraint is the issue. Under the hydro constraint, if I focus more, in the next chapter we will be doing it, the inflow rate of water to the catchment area. The outward flow of water from the catchment area to the hydro system. Then loss of head, any habitant getting affected, any kind of generation set point changes. All these aspects definitely cause changes in the neighbor. So these constraints must be kept in mind before I go for commitment of generators for a certain schedule. This is also important. With the perspective of hydro only, perspective of hydrothermal, the hydro water related constraints are very important and serious aspects. Another is nuclear constraint. Suppose this is specifically with the nuclear plant is part of the system. Another constraint is added from this perspective. A nuclear plant has to be operated as a base load plant only. This shall be constantly put into service the certain accepted radiation level in and around the generating plant. It should be put in service. I cannot use it as a top-up plant. What do you mean by top-up? When I have a load curve on the station, when I divide that load into 3 sections, the most lowest load be addressed by base load generators. The central part of the load curve be addressed by intermediate load, and the topmost crest part of the load be served by peaking generator. In that 3 bands of generating categorization, so nuclear plant and hydro plant serve as the base load because they are put to generate constant megawatt output with respect to the permitted availability or permissions granted to this. So this is another aspect. I cannot consider it as there is a change in load, I shall generate more and more. It may be due to nuclear constraints or due to fuel storage or availability of fuel, whatever the constraint. Another important title we find in the unit commitment constraint is must run. So this is something called as tag. This is a bold assigned to a certain generator in a plant. This is to say must run means don't touch, reserved for. How do you find some instructions on certain avenues? Like that, must run the unit means certain generator in a plant. Among the committed generator is said as must run. It means it should be running continuously over the period it is expected, planned to support the voltage profile of the system with a stability aspect. If this generator is not maintained constantly over the specific expectation, it may not be supporting the variation in the voltage happening due to any adverse phenomena. This is identified as by having it run continuously, it has a greater support to voltage profile to the stability point of system. In this way, must run. You may ask me, if it is a must run, how would the economy be considered? Absolutely correct. Must run shall not mean it is simply to run however I like. It is to keep in concern that this generator being put in force kept on an observation, economy, as well as voltage support. The voltage support is because any inductive or reactive power requirement changes in the power system definitely adversely affect the voltage. If you in turn try to adjust the voltage, definitely active power delivery gets affected. What is an active power delivery from machine 1 to machine 2 in a power system? Suppose I have 2 buses. Bus number 1, V1 voltage. Bus number 2, V2 voltage. Connected by a transmission line, reactance say X. I can say power transferred from bus 1 to bus 2 is V1 into V2 divided by X12. Transmission line, total reactance X12. Find up the delta 1-2 between power angle. Here comes for the active power delivery also, V1 and V2 terminal voltage have come into picture. If there is a dip in voltage, is it not that P is also getting affected? If P gets affected, frequency gets affected. See how the connectivity between P, Q, V, delta in the power system play a vital link. So therefore, it is very necessary to maintain the voltage in the system to the suitable specification and the tolerances permitted. In this due regard, certain generators are identified as a good background support for that feature. In this due respect, it must be kept. And rather, you can see system stability is of greater importance. While doing the transaction, if a system is getting affected, security of the system is being lost, then what is the fun of operational power system? The securedness is due to the connected devices getting secured themselves first, securing interconnection being more and more highly desirable to meet their requirement. Otherwise, one-to-one failure may lead to disaster and loss of stability. Hence, it is technically a feasible state that some of the identified generator must be run continuously to keep the voltage support for the requirement. This is another critical issue, fuel supply constraints. Now let us say a thermal plant where coal yard is having a shortage. The delivery of coal to the plant or yard is not frequent, it is coming intermittent, and you have a deficit of coal to fire for the required target of generation. Or for a fuel like a gas or oil fired plant, the support from the fuel supplier company is not getting reached to the requirement easily. Deficiency of fuel is the challenge. Then what should be done? You cannot develop power from certain plants, then that is called fuel supply constraint. You must plan and flexibly change your schedule according to this, such that such an compromise in a generation shall be taken care by another generator of the different kind of fuel, so that you will keep on running this plant continuously, at least till the fuel is reachable to your plant. This is how a systematic planning of a fuel constraint has to be taken into. It may be due to oil or gas, or it may be coal. You must see to it that your planning of availability of fuel, plan of a particular generation, consumption of that over a period, how long it will be exhausted or how long it will run before the next lot of fuel comes to our plant. This must be taken care without fail. The another is transmission line limitation. This is a very critical issue. However, huge resources, abundant resources, if I have with me for a generation, I cannot transmit every kind of power which I have generated to the system unless and until I have transmission mechanism capable of doing it. Because transmission mechanisms or transmission system is interconnected from bus to another throughout the system to reach the requirement of an end user. So there is a limitation of transmission line conductor capacity, often called as bottling of reserves. Sometimes what may happen, the resources which are generated are capable of generating and not able to connect it to the grid and deliver to the grid for the next part of the requirement. So transmission line poses a limitation. You higher and higher megawatt what we generate should be dispensed on other side, then only the generation has a meaning. So this becomes bottling. Those reserves become centered single side, it cannot be taken dispensed on other side. This is called a bottling. So this must be avoided. I should have sufficient capacity from the generating perspective, able to dispense that generation to the grid so that it will be disseminated into the grid on the other side for the proper distribution. This has to be planned very suitably. Whenever a power system operator plans for the future expansion, they will focus on this. Is my present transmission mechanism grid is sufficiently trendier enough to focus for the future plans of generation, or any additional infrastructure need to be incorporated? Or how is that the additional generation I should reroute so that bottling of resources will not happen? This has to be taken care systematically, because when we consider only cost of generation and economy, I will not be taking care of the best path. When I take a best path, I will not look forward to who is generating it. When I combine together, this issue comes into. When I want to make every transaction what I am doing be more profitable, these are the technical limitations I will encounter. So these encountrances must be properly tackled and should be seen such that their suitable remedials are maintained to see to that it is cost effective. So these are the few technical constraints. There could be one good question for you, the least, and explain the constraint related to unit commitment. You shall take one or two lines of each presentation for the constraint. There may be another constraint which is explain what is spinning reserve. specific question. I was speaking over here only. When I wanted to explain this spinning reserve, I have a separate slide for spinning reserve understanding. So here is the slide. What is spinning reserve? What is the importance of spinning reserve? Explain with an example would be a question for you. Then how would you explain this? To explain this is a case study. As we were interacting, spinning reserve is a ready-to-use energy pair which is being generated in the generating plant while meeting the requirement of the current load. This is to substitute sudden change in load. Suppose there is an increase of load, system is able to cope up without switching on any additional generator. Or the spinning reserve is by value such that suddenly one of the generator in the system decreases the output megawatt due to internal or external causes. That deficit megawatt from that particular generator is adjusted, cope up by remaining generator by proper tuning of them so that system finds immediately a normal mode. This is how to meet that aspect of balanced delivery, spinning reserve plays a vital role. Hence, spinning reserve is a reserve generated energy available in the system ready to wheel upon, ready to draw as and when a critical issue like step change of load or loss of generation, failure of generation is noticed, system is able to cope up with the existing mechanism. This could be the explanation for spinning reserve minimum. Then let us take an example where I have two reasons. This example is taken from Wood and Uhlenberg textbook. So we have two interconnected generating regions. Region 1, western region, region 2, eastern region, connected by transmission line for interconnected operation. Here in this plant area, geographically A or western region, I have 3 units, generator 1, 2, 3, and in this eastern region, I have generator number 4 and 5. So there are 2 generators, there are 3 generators, and there is a load in this, there is a load in this. So system is agreed upon interconnected mode of operation, because sometimes it is profitable rather than setting up a new generator, borrow the power and meet the requirement. Sell the power if you have excess generation. In that due respect, interconnected mode of operation is beneficial. So in this way, if I focus, let there be 3 generators, let there be 2 generators of specific capacity. Then the transmission line laid between these 2 corporations is known as tie lines. Tie lines are the transmission infrastructure, like a transmission line only, there is no change. They are meant exclusively to sell and borrow the power. The main task of or purpose of installation of these transmission infrastructure is to sell or borrow the power among the corporations. Within each corporation, we have transmission grid, generator, load, etc. This is an area itself. This area is able to interconnect to a neighbor for a profitable exchange that is called as a tie line. Then what are the characteristics of these generators? So this is being given. Transmission tie lines join the regions may transfer a power up to a maximum of 550 megawatts. The limitation of transfer of power either side is the capacity 550 because of the loadability of the transmission line conductor, 550 megawatts. And 5 units have been committed to supply 3090 megawatts as per table. How is that? Let us see what each generator is capable of, what it is doing in this way. So table is framed very systematically. Region, area 1, area 2. Region, western, eastern. Under the western, I have 3 units. It's called unit 1, 2, 3 under this heading. 1, 2, 3. Unit 1 is capable of what capacity? 1000 maximum. 2 is capable of 800 maximum. You might ask me, how do you get this? This is a typical example to narrate how is that spinning reserve energy saved, safeguard the loss or excess requirement effectively is to understand. Then 3 generators of capacity 1000, 800, 800 are there in the western region. And in the eastern region, 4th and 5th number 1200 and 600. Then, right now in this region, what is the load? You can just go here. Regional generation, regional loading. You can see this column. In this western region, there is a net load of 1900 megawatt. Then for that, what is the generation taken in 1, 2, 3? It is given here. Unit 1, which is of 1000 megawatt capacity, typically a state is observed, it is producing scheduled to generate 900 megawatt. Second, which is of 800 capacity, scheduled to 420 megawatt. Third is 420 megawatt. Total generation in the western is 900 plus 420 plus 420 refers to 1740 megawatt. But what is the load available? 1900. So 1740 is the set point to generate and deliver, but load is 1900. What is the mismatch? Mismatch is known as deficit generation. You may ask me, why not to generate more and more here and meet it? It is a case study to explain how a floating energy can be utilized. This is one economic solution, 900 megawatt from one, 420 from these two. If they are in service, may the production is economic for certain concept. In that due respect, let these three generate 1740 megawatt against the load of 1900 in the western. Then the difference between these two is 160 megawatt. Then 160 megawatt is a shortfall. How do this will meet? Either it should generate more and more or borrow it from other. So this we want to understand. Let us take 1740 is the generation, 1900 is the demand, difference is the deficit 160. There is another column over here which is called reserve from machine number 1. Machine number 1 is having a capacity 1000, generating only 900. What is the state it can generate now? 100. Then machine 2 is 800, 420. The remaining is 380. And machine 3 is also having 380. There is a spinning reserve available from these machines to take into account by 100 megawatt from first machine, 380 megawatt from second machine, and 380 megawatt from another machine. So it's called 380, 760 plus 1. 860 megawatt is readily available from this particular area if I want. Another aspect, just see in eastern region. In the eastern region, I have two generators. For example, 1200 megawatt is developing only 1040. And another generator fifth is 600 megawatt developing 310 megawatt. Together it is generating 1350, 1350. The load in this area is, say, typically an exercise is done lesser, 1190. This is having excess generation. 1350 minus 1190. This is mathematically adjusted such that 160 is the excess power over here. So this can export. This area can export 160 megawatt if somebody is in need. That is the reason this spare energy in this generation area can go out of this to area AR1. Then, meantime, I can see any 160 variation. Suppose it demands 200. Is it able to cope up? 300 megawatt. Is it able to cope up? That is to be checked again by its capacity. The spare capacity from fourth machine is 160 megawatt. From the fifth machine is 290 megawatt. So I have here 450 megawatt excess energy from the eastern region it can deliver. Right now, 160 megawatt is being pumped to make it balanced. So this 160 megawatt, if I allow to float, the current generation will borrow 160 megawatt, balance their load. Suppose the load in the area 1, western, still increase 2000 megawatt without changing the set point. What I can do? I can make the set point change in the area 2. I can pull or pump higher power here. In this due regard, I want to narrate. Let us say column-wise accumulation. The total capacity available in the total A and B generation or western eastern is 4400. Total output in cash is 3090 megawatt. Okay, it is nothing but sum of the generation right now. This matching. the total spinning reserve available in the entire system of A and B or western and eastern is 1310. There is a possibility of the exchange of 1310 megawatt among them if there is an requirement. But it is not that entire 1310 I can encash due to the system area load. So again I have regional load of 3090 matching. So it is being matched so perfectly by this. Now let's say a case study. Suppose there is a drop of certain generator megawatt 420 here. Suddenly this generator fails. 160 megawatt is borrowed from here and 420 megawatt is crossed. Can it generate? Once it is gone out of your generation, 420 megawatt is your output loss. See to this, 160 plus 290. This is a megawatt. What is that extra available can flow out of this to the neighbor corporation to make its requirement as available. But there is an issue of pumping the power by the transmission silent ability 550 megawatt only. Suppose there is a loss of 600 megawatt generator which is developing 310. 310 is lost. Can I generate from this area western to pump power backward to eastern to make it loss? I can definitely do because the capacity is 550. See to it that if there is a loss of 1040 megawatt generator in B, this is lost. I cannot meet the requirement. You can see here 1040 megawatt which is producing from fourth generator. Even though I have a generation 420, if I make it to run fully capacity 1000 plus 800 plus 800. So I will be having 2600 megawatt generation from this area. If the load is 1900, remaining power I can pump here, but I have a limitation of transmission. I cannot fulfill the loss of fourth generator in the interconnected operation by spinning reserve energy. Hence, spinning reserve is a critical energy to be spread in both the areas such that certain loss in each area can be adjusted themselves and by other by cooperation. This way, the exchange of power via the tie line needs the knowledge of spinning reserve. Let us put some more case study over here. You can see, verify this scenario. Generation of largest unit is 900 megawatt. You can see here. This is 900 watt. Highest generation in the plant is A and B. If I consider 900, you can just see. Available spinning reserve local is 760 here. This is 760. You can see 380 plus 100. This is 760 is a megawatt exchangeable available between these two. Okay. Locally. And silent capacity of 390 because already 160 is being encashed. So it is a power available. This western can pump if required. A 390 megawatt variation in eastern region can be helped by taking suitable generation at western region via the available mechanism. But in the eastern region, 450 megawatt. Total is 1150 megawatt load can be supplied. So in the eastern region, in this region, if I speak about, look at this, generation of largest unit is 1040. Okay. 1040. Available reserve, local it is 450. Silent capacity is 550. It can pump to the eastern to western region by capacity of 550. But western region is having 700 megawatt in that frequency. So total of 1000 megawatt load cannot be completely supplied. It cannot supply because of the limitation of 550 megawatt. I cannot supply this 700 megawatt due to the limitation of 1000 excess. 1150, what is there? 550 being my limitation, I cannot deliver this load. It means the limitation of the spinning energy come into picture with the silent capacity. Therefore, it cannot supply. So, lack of 40 megawatt of spinning reserve in the eastern region can be applied. So it means it is a narration. What we can see here, just see. Suppose there is a loss of any one generator here. By suitable increase of generation to its full capacity and borrowing of power from neighbor can be worked out. Numerically, we can say, if this 420 megawatt generator is lost, what I can do, fullest capacity, 550 megawatt, what it can supply highest, I can borrow the loss of 420 and its load and remaining deficit, I can increase at a set point here. I can balance the system. Loss of any system in A can be worked out by spinning reserve. Numerically, if unit 2 is failed, it is possible to maintain still a balance of delivery of load, borrowing the power and increasing the generation here. Other way, loss of fifth generator can be cope up by increasing generation and borrowing the power. But loss of fourth generator in the system cannot be managed. Technically, 1040 megawatt loss you cannot fulfill either by increasing to the fullest capacity, either A is western region and in the eastern region by second generator, because there is an issue of transfer of power only by 550. You can see here, highest is 600 it can generate. Then how can it will make 1040 substitute? 1040 substitute it cannot do. So 290 it can support. 310 is its capacity right now. 210 is a spare available. 210 plus remaining amount which can come from western to eastern can only make the matching of this one. It is not possible because 550 is the highest. 550 plus 290. What you can match? You cannot match 1040. That is the issue called as bottleneck issue when studying the spinning reserve. Hence, spinning reserve must be allocated equally or properly to all the such areas to see to it that any loss of generation, sudden change in load is able to cope up with the systematically available resources. This is the best example one can practice, or similar example you can make a tabular form and narrate certain loss can be fulfilled, certain loss cannot be fulfilled. That is called as issue related to bottling or botting. Then moving to the next heading, thermal constraints. When we were seeing thermal constraints, startup cost and shutdown cost are two important aspects. There could be one good question, what all explain the thermal constraint related to the power system by the following aspects. When we have a startup cost as an heading, it is the investment cost incurred in bringing the thermal unit from the cold room temperature to the working temperature online. Whatever is the investment we put into bringing that cold start from the room temperature to the online is not yet returned to you. Once the machine starts developing megawatt and being sold, it is returning you. Till that point of bringing it online, whatever the investment we put into that plant is called as startup cost. Similarly, when I took a case that shutdown, from the point of withdrawal from the combination, machine is decommitted till it is brought to a certain working temperature, be there, is called as a banking, or cool it down to room temperature. It's called cooling cost. It is not paying anything for you. That is the reason minimum uptime, minimum downtime are placed as a criteria. So therefore, why we are concerned with the thermal constraint means startup cost, shutdown cost adds value to your system. Therefore, these must be recovered properly by keeping the system in proper duration as a service hours. Hence, this is important. Then, suppose imagine you are trying to start a machine from the cold start or from certain temperature. It was previously withdrawn from the schedule, not maintained to room temperature, maintained little higher than room temperature. We call it as banking. Let us see what is that. So, startup cost, investment put in bringing the machine from the room temperature 25 degrees centigrade to online to develop megawatt. That is called as a startup cost. So when it is involved, when it is being cooled down to room temperature, it has to be start up from room temperature. Then the cold start cost incurred in setting up or bringing the machine from room temperature to the working temperature, say cost incurred cold, from the cold to working temperature is by an expression fixed cost, P fixed. Certain value is evaluated as a fixed cost plus to heat up that mechanism to bring their working temperature gradually to the online required temperature. It is called investment of fuel and latent heat and all such thermal parameters which are playing has to be taken in this case. That's called as fixed cost plus fuel cost into the bracket heat H cold and an expression 1 minus exponential minus T shutdown divided by coefficient of temperature, right, alpha. So this is a typical thermal expansion, thermal expression, which is being used to compute cost incurred in bringing that machine from room temperature to the working temperature. Then this is put as a graph. You can see startup cost on a vertical axis and a horizontal line time independent of hours in duration. So you can see the blue line. Blue line is just an exponential like this. So certain point, fixed cost. It is a fixed cost rupees plus what is that temperature you would like to rise from current temperature. That is an investment. Once it is brought into later after 6 hours break even, that is profitable. Means this is the hour minimum you need to make it later profitable. Suppose this particular machine which I want to take on is said to be not in the room temperature, certain 400 degree centigrade maintained. We call it as a banking. Let us understand banking. Imagine there are 5 generators running for my schedule. At certain temperature they are working, developing power and load is decreasing on the plant. It is decided that for the next 25 hours, I do not require machine number 5 and machine number 5 is said to be taken out of the combination. It's called as a decommitted and it is taken such that after 24th hour, 25th hour, 2 days later or 24, 1 day later and the next day, it is required for the expected change in load. Only for 24 hours it is not required. 25th hour it is required. Then it is not advisable to shut it down perfectly to the room temperature because the cost involved in cooling it to the room temperature, bringing it online again becomes very cumbersome and costlier. It is not advisable because of the minimum uptime, minimum downtime issues. Let us say, rather than keeping it cooled down to the room temperature, maintain burning the fuel reduced by quantity, maintaining it at certain lesser temperature so that you are keeping it spinning. It is running with the minimum fuel of the minimum possible so that on increasing the fuel to that, it is ready to come to your online state with a lesser amount of duration. It means banking is the process of maintaining a decommitted unit at very lesser temperature than the working temperature, burning the minimum fuel, which on requirement by increasing the conditions, fuel conditions, it is brought to online immediately. Cost of bringing banking to the online is lesser than bringing a machine from room temperature to online in terms of investment, in terms of hours of requirement. That is how cooling and banking are compared. Banking is nothing but a machine which is just taken out of the schedule. Rather than cooling it down to room temperature, maintain it at reduced temperature, make it running continuously, keep on spinning continuously with the minimum input fuel to that. So that after a certain number of hours, it is again pulled on to the service. That is called banking. If you are banking a machine, you are requiring it on, then cost of start startup cost by a machine for a machine which was just maintained banking is C banking. Cost incurred in putting that machine online which was previously taken out and banking is by expression. Which is again, you can see red line here. It is fixed cost, C fixed, plus the coefficients concerned to thermal ratings of that. It means this red line shows a particular banking curve of a thermal unit. On comparison, suppose a generating aspect is maintained perfectly cooled down, the same machine is studied for banking at certain lower temperature and its cost comparison for hours of time. You can just see. Suppose you are trying to make a machine to go under the room control. You can see. The cost of that to restart it minimum 6 hours, which is rising very high. If you are not requiring it for 6 hours, 8 hours, 10 hours, better is to cool it down. This curve shows. If it is banking, you can see it is rising like this, slow. So we have to take a decision. For me, certain generator, when I want to pull out of the decommitment or commitment schedule, later when I require it, how long I keep it out of my service, that duration we have to see. Later, which point, break-even point, if it is a cooling you have taken, when later I can use it. If I take it as a banking mechanism, which is profitable. I can say banking is profitable for hours immediately once the shutdown has been taken. Just within 2 hours, I am pulling it back. You can see this is lesser in dimension. It's a cost and duration. So red line is below this. This is better to bank it. You require 7 hours, 10 hours later. You can see this is rising up and blue is going down. So cooling is better. So in this way, judicious decision can be taken to decommit a certain generator when you require it next, after what or how many hours later you require. So whether to cool it down is profitable and start afterwards, or keep it spinning with a minimum fuel is profitable or not, is understood by cooling and banking mechanism. And those will become our input when I start a machine, thermal unit. The cost incurred in setting up that from cold start to the working temperature, the green line, blue line follows, and which was previously taken just last few hours back, and again I raise the temperature and finally I require, which is profitable. So startup cost comparison comes into picture. So this one page which I am trying to project is one good question itself. Explain the thermal constraint like cooling and banking of thermal unit. So you shall have this curve and one expression for each. Definitely make the mechanism. So depending upon the type of generator, later how many hours I am in need of that, decision can be taken whether to cool it down or to bank it, and cost incurred in bringing it online differs. The difference is whether you follow cooling curve theory or banking curve theory for your start. Next one. Then commitment solutions. So commitment solutions, as in the earlier class we started, brute force method called a simple enumeration method. In line with which again I have simple methods called as priority listing method. What is this priority listing method? Suppose you have been given in a station or number of generators to you and their fuel cost functions were given, average production cost. What is the cost of production per megawatt of that particular plant? How the load is changing? How you will start pairing the generator as the load step changes? So this is nothing but commitment of generator for a change in load and decommitment as a load decreases. This has to be solved systematically. The method one what we have seen was brute force method, simple enumeration. The another method what we have is priority list method. What is this priority list method? We know that in a generating plant, even though machines look identical from the manufacturer and capacity perspective, the performance and cost per megawatt differ when they start developing the output. Depending upon the production cost from each machine, priority listing method is chosen, which is that like this. So we have to see, just let us see one example and come back. Priority listing method. Imagine I have been given 3 machines in a plant. How do this priority listing method work? I have to see how the production cost of plant 1 generator for a load capacity minimum to maximum, plant 2 means second generator, third generator works out. Suppose if you have been given 3 generator an example for a range minimum to maximum, average production cost of plant generator 1, generator 2, generator 3 is taken here. Full load average production cost. Machine number 1 for what capacity? 600. It is 9.79 rupees per hour. The second machine for a full capacity 400, an example 9.4. The third machine 11.1. By this, what is your observation? The average production based observation is categorization on priority. The priority shall be sorting them on the basis of minimum fuel cost to highest. In this order, if I see second machine is lower by production cost, I give a rank number 1 for it. Strictly if I order them, machine number 2 becomes first priority for me, machine number 1 becomes second priority for me, machine 3 becomes third priority for me. So what I did exactly? Not enumerated, not computed anything from this. I just studied the average production cost of these 3 machines and I arranged them on the basis of priority, lower the production cost, incremental, lesser. Then from this, what I understand? Suppose the machine 2 is having a priority, look into the capacity. For a capacity of 100 megawatt to 400 megawatt on the station, my choice has to be machine number 2 till 400. If the capacity of load increases beyond 400, I should combine machine 1 with that. What is that? Second priority is machine number 1. Capacity is more than 400, pull in first machine. Till what combination? 400 plus 600, till 1000 megawatt. If the load of the station is still increasing beyond 1000, I have no option, third machine I have to use. So this is how 400 initially up to and later 400 to 600 and 1000 to 200 is the range I will be getting from this. This has been put in the table like this, ignoring minimum downtime. So startup and shutdown costs are not considered. Simple mathematical work has been done. You can see here, the first most priority at the downside is 2. Minimum of 100 to 400 machine 2 can deliver. When the load is increasing beyond, I have to combine machine number 1 with the 2. From the minimum of 100 plus 150, 250 is the minimum, 400 plus 600, 1000 is the highest combination. So 250 to 1000 is the pair 1 and 2 can share. Once the third priority is 3, load is increasing more than 1000, I have no option, machine 3 has to be combined. When machine 3 is combined, what is the minimum generation? 150 plus 100 plus 50. It becomes 300 megawatt minimum. These 3 together can share and maximum of 600 plus 200 is 1200. So it's very simple. What I did is priority listing method is from the average production cost perspective, the machines must be segregated, ordered on the strict priority till their minimum to maximum capacity, they must be maintained and incumbent generator to be combined to pair for a certain combinational load and further and next, etc. This is one side of priority listing method. As the load increases, this is the pattern. Other way, load can start decreasing. Then look into this priority strict order, 213. If the load on the station is not 1200, it decreases to 1000. So I should remove the latest machine which is added. Third machine, remove this first. Then 1, then 2. It is because by the order itself, the most first machine is fuel cost effective. The second is little costlier. The latest is costlier. Then the costliest pair must be taken first. Then the inner like this. This is called following the shutdown rule, priority wise, which is costlier should be taken out, which is lesser than that, and the least one should be maintained. This is the gist of priority least method for a certain minimum to maximum capacity. The same thing has been presented over here. The priority listing method follows a simple shutdown rule, and it has to work out average production cost of the machine from minimum to maximum and pair them accordingly. Let's see the theory behind it. Explain priority list method using a flow chart. This was a question you got in the earlier academics itself. Let's see how it starts. Initialize your setup. Start your functionality of the algorithm. Then see, calculate minimum number of units that must be run to carry the load plus spinning reserve every hour. This is your first task once you decide your system. Once you decide what is the number of, how many number of machines you require, what is the load, what is the spinning reserve. Then at hour to hour, as an hour of your observation of the station, next hour, hourly if you are observing, next hour, the same status may not remain. Check it. Compare number of units running during this hour with the minimum units required for the next hour. I should keep checking the current 6 generators which are running for my 60 minutes of duration. For the next 60 minutes of duration, do I really require all these 6, or I need to reduce the number, or I need to increase the number of generators? Decision has to be taken. In every hour I should take this. When I take a decision may like this. Lesser units are needed. Load is falling. Then I need to reduce the generator as per the lesser demand. So if that is the case, my decision go in this line. Like this. If there is no change in load, there is no significant change, may I maintain the same number of generators? My decision goes here. Same number is needed. I just go this way. This is my path of decision. Then decision may be like this. Load is incrementally increasing. Additional generation is demanded. You can see more units are needed. This is how I can. So from this decision, I can have 3 paths. Reduce the generation, maintain the generation, increase the generation, add the generation more and more. Then see to, let's say, increasing is expected. More generators are required. Then add a generator. Before that, start up units to meet the requirement. So I should see which generator I have to pull into the combination, so that whose capacity when I add to the existing hour capacity become my requirement. Then calculate total cost. When I use the decision, add a generator, expect its total capacity, cost of production, then come, is this period complete? 1 hour of your expectation is run out, exhausted, come down here. No. Is it complete? Yes, means somehow committed, units are hourly, entire period. Then it may say, hours are not complete. Still I am in a out of 24-hour schedule, may I am in a 8th hour, 9th hour, 10th hour, 11th hour, 12th hour, I have to go further. So when I complete, is it a complete period of your observation? No, only 1 hour I did, 1 hour I managed, I go back. No, go to the next hour, 9th hour, where I come. During this 9th hour, how many units are running? Is that capacity of generation, reserve is perfectly okay? Then check this. Is that adequate that the current 9th hour setup is requiring an additional generation, either to maintain the same thing or reduce the generation? Again, I take a decision. Then let's say 9th hour, there is no incremental change, it is maintained. Then I may go this way, same number of generator I maintain. I come down, no change in commitment. Then I come, is it the complete? No, I am in a 9th hour. 10th, 12th, 13th, 14th, 24th, I still have to go. Then I come down. So I go next hour, 10th hour. Then in the 10th hour, is the generation number, load, spinning, everything is okay? Take the decision, is my 11th hour is perfect? No. Generation is more than load. Load is falling down. Then decision is something like this. I need to reduce 1 generator. By chance, lesser units are required. Then I come down this way. come down. Then it is compare number of units running right now and that required in the next H hour. This is a decision, because when a decommitment is to be taken, when I want to reduce the generation, generator needs to be taken out. When I want to take out, I have two ways. One is to cool down or maintain at banking. This is what just now we have seen. Cooling of generator, I mean setup, or banking it certain reduced temperature. How long that particular generator which I decided to withdraw is not required H hours. I am in the 11th hour, up to 2 hours, up to 14th hour, I don't require. For 2 hours, I don't require it. Then I have to check, need fewer units for part of the H hour. If it is so, no change. Suppose within a 2 hour only, I may require this machine back. Then don't take any shutdown. Don't make it spinning, so that your control is not to change like this. Again, you are in the 12th hour. 12th hour, again assume that generation is okay. Suddenly load is falling. Again, you may find a situation, reduce the generation further. You come down. Again, you will see, no, load is reducing. Probably keeping the generator is not economic. Decreasing the generation, making it to shut down is the better thing. Then you will not run this way. You require next 10 hours, I don't require the generator. You decided on the plant prediction. Then you will not go for upwards, it will come there. Need fewer units for next 10 hours. Then for next generator, so that I will decide this generator has to be taken out. Then I decide shut down unit based on priority. Which is that generator you want to really take down for a next 10 hours or a next H hour, not required for you. Taking them out is a cost-effective measure for you. Take a decision, record shutdown time and come down here. So you have come to the 14th hour, you decided, still your computation is not completed. Then you go backward. Then 15th hour, like that, you have to take a decision. Let's say your entire schedule has come to end of your observation. Yes, this is my final 24th hour, I come down. Give the commitment schedule, hourly entire load schedule. This is how priority list method is put in the form of sequential flow chart. It means initialize the system, get the average production cost of them, calculate number of generators required and spinning reserve required, take a decision, current mechanism is making your sense, excess is there, lesser generation, same generation to be taken, and make this cost to happen, decide your entire schedule, come back and complete your task. This is the simple flow chart for priority list method. Preferably in the examination, you are called to explain priority list method with the help of flow chart. This is a flow chart I have taken from Dr. K. Umar Rao's textbook. Please present similar textbook presentations only. Okay. And in line with this, I took an example. These were 3 machines. Capacities were mentioned and their average production costs were given to you. And I have shown you from the problem, this problem is taken from Wood and Uhlenberg problem, the solution I have taken. So this was given like average production cost. I categorize them on the priority. I start combining them for a step change of load, taking the 100 to 400 and 400 onwards, 150 to 600 and add up. You can see here. First I call machine number 2 for this range. I add machine number 1 to that. This is the range of operation. And I add machine number 3. This is the range of operation. This way, when I combine 1 and 1, this is a schedule. As and when I require to decommit, I remove from the top, which is the latest added machine to be removed first, because it is a very costly machine you added on your priority. You kept on adding the component on the basis of cost, which is cheaper, the first. Next one, incrementally costlier. The last one, most costlier of your system. This is how the simple problem, one sample approach, you need to categorize. You will be given a numerical access and you have to categorize them. You have to write this table and you have to narrate this table accordingly. This is the task under priority list method, which you were familiar, and it is my concern to see to that still you become familiar and able to present in an effective way. And I have another problem. How exactly my explanation has come to my words like this way. Take an example, machine 1 with a max capacity 600 with a fuel cost, unit 2 with a 400 with a cost function, machine 3 with a cost function and capacity. How do you allocate megawatts? How do you work it out from priority list method? Let's see, I have knowledge here. Full load average production cost means production cost corresponding to full load divided by full load. For the value I have mentioned, this value full load divided by 600. Production cost for you have to put here 400 you have to put here, 600 you have to put here, 200 you have to put here. Value will get that divided by 200, that this value divided by 400, this value divided by 600. That gives you average production cost. That's what is mentioned here. Production cost corresponding to full load divided by full load value. That is the value you take to categorize. Hence, I have another example, fuel cost function, their capacity. I will use this in the position P, P, P like this way. I will get P1, P2, P3. I categorize them. Let's see how I will do. This how we can. Full load average cost of production for the machine number 1. Wherever I have a P, I substituted 600. Wherever I have a P, 400. Wherever I have a P, 200 for machine 2, machine 3, machine 2, machine 1. Then I could get their values comparative to me. On this strict priority, when I check visually, I will find machine 2 cheaper compared to other 2. Hence it is a priority unit, rupees per hour, capacity maximum. I can table it. So 94.01 rupees per hour as a machine 2 as my priority. Next priority is 97.22, machine number 1. And the last priority is machine number 3. Then with the machine number 2, what is the capacity I can share? Up to 400. You can see. With the machine number 1 combined to which has ability of 600, total 400 plus 600 I can see. And machine number 3 is having 200, it can follow individual 200, but with the pair 400 plus 600 plus 200, it becomes 1200. This is another simple view from book to book. You will find a priority listing problem. This is how the shutdown scheme or particular priority listing method, ignoring those things, is given. Combination, demand. So priority is 2. When the priority is 2, up to 400 it can serve. 2 and 1 combination, 400 to less than 1000, because it is 400, its capacity is 6. When I add, it becomes 1000. Up to 1000, 2 and 1. 1000 above, up to 1200, 2, 1, 3 combination. Then it is a shutdown if I want to take. Load is decreasing. Remove 3 first. Remove 1 later. Remove 2 later. So withdrawal is reverse. So it should be a startup combination. Commitment in the order of priority, decommitment in the reverse order, because the very latest added machine is costlier. That has to be eliminated first, is a rule of priority. This way, another example is cited for you. Next one is the most priority scheme around the simple shutdown rule algorithm might operate as follows. It means to say, sometimes it becomes very cumbersome. When you have a priority rule method, determine how many hours H later or before the machine which is assumed to be taken out, it should be taken from the decommitment, whether to cool it or bank it. Depends on the cooling and cost, or banking cost method based startup. For that method, this page is dedicated. This page is dedicated to see to that the process of withdrawal of a generator based on How many hours of service you don't want? Later you really want it. Is it really within its turn on or on time or shutdown time duration? That you have to concentrate and see to it that removal is profitable or making it banking is profitable is discussed over here. The same thing